Hello gems, welcome back to another video. In this video we will be discussing all the derivations from the chapter of current electricity. In the previous video we discussed all the concepts from this chapter, so if you are interested in that, the playlist link will be available in the description box below. Okay, so with that being said, let's begin with today's video. To these first two derivations for the day, actually these are not derivations as such. We'll be obtaining a relation for average current and instantaneous current from its very definition. Okay, this is not like a derivation, but we will be using this terminology, so it is important. So we'll just quickly go through them. Okay, so first we are going to obtain a relation for average current. Okay, average current is basically defined as the amount of charge that passes in a particular interval of time. Suppose we have a cross section area A, the amount of charge that passes through this cross section area is suppose delta Q in time delta T. Of course you need a time interval to measure how much amount. Okay, so the amount delta Q passes through this cross section area A in time delta T, then the average current will be the amount of charge that passes divided by the time it takes. Okay, the time interval. Okay, so the amount of charge by the time interval will give you the average current that has been that has passed through this area. Okay, now for the instantaneous one, if you want to find current at a particular instant, you have to make this time interval very much tending to 0, right? So if the time interval is 0, you will reach a particular instant, right? You'll get the current at a particular instant. So if you make this delta t tending to 0 in this definition of time, you will in this definition of current you will get instantaneous current, right? This is nothing but definition of your derivative. So dq by dt, the rate of change of charge, gives you the instantaneous current. Okay, so if you are given q as a function of t, you can take dq by dt, that gives you instantaneous current. Okay, let's come to current density. Current density is basically denoted by letter J. Okay, current density, right? So current per unit area, how much current is there in a unit area. So actually this J is a vector, you can obtain its magnitude as such, right? Current divided by area will give you current density, its magnitude, or you can write this I as a dot product of J and A, right? Area might think it is not a vector, but it can be treated as a vector. You can take the direction of the area vector to be normal to the surface. Okay, so suppose this is your area A and current is passing through this area like this I, then if you want to find the, basically this J will have the same direction as that of current. Okay, so you can say instead of I you can say J. Okay, and the area vector will be perpendicular to the surface. The surface is like this, so the perpendicular to the surface will give you the area vector. The angle between them is theta. Okay, and J dot A, which is J A cos theta, which you can see will be along the direction, right? Along the direction, J cos theta will be perpendicular. So J cos theta will give you the current. Okay, so if you see a case like this, or basically by magnitude, if you want the current density, it is current per unit area. So these are a few terminologies that we will be using in our derivations. Okay, and it's important to know them. So let us begin with the actual derivations now. Coming to the derivation on drift velocity, in the previous class we saw that the electrons inside a conductor under the influence of electric field, which is due to the voltage applied due to a battery. So under that influence, these electrons will not accelerate, right? They will not be accelerating, they will actually move along the conductor with some constant speed, which is known as the drift speed, right? This was the theory behind your electric current. So we'll be finding the relation for drift speed, which we learned in the last class, which was minus E tau by m, and we'll be actually deriving it today. So let us start with the derivation. Suppose we have a conductor, this is inside of a wire. Suppose we have electric field which is set up due to the supply voltage applied to the conductor. Then if electric field is like this, electrons will move in the opposite direction, right? At least that is what we assume. So the acceleration on the electron due to the electric field, so acceleration due to electric field will be given as, so you basically know the expression for your force, right? It is Q into E, QE, right? F is equal to QE, and here F will be equal to minus EE. right? Charge is negative and charge is minus E, right? Electron. We are studying the electron over here. So electron is minus E, and we have electric field. This is also showing that the force on the electron due to the electric field is in the opposite sense. Force and electric field are in the opposite direction due to this negative sign. Now we can say that force can be written as mass into acceleration, right? And this will give you EE, right? So acceleration will be given as minus E by m, right? E capital E by m. Okay, so acceleration, since force is opposite, acceleration is also negative. Okay, so this is the acceleration on the charged particle on the electron inside the conductor due to the electric field which is present due to the battery voltage. Okay, so this is your expression for acceleration, right? So your charge should be accelerated. Well, that is not the case, because over the interval we'll see that it suffers collision, right? Inside the conductor, it suffers constant collision with the parent atoms and the other electrons. So we will assume that time t1, so we also have to consider the collisions now. So we'll assume that ti time, some time ti has passed after the recent collision, after the last collision. Okay, and we'll be using Newton's law, the equation of motion which arises from Newton's law. So Ti, some time has passed after the last collision, so the electron has suffered the previous collision, and the time elapsed after this collision is some Ti. Okay, so Ti time has passed after the last collision. There is no collision in this time Ti. Okay, so in that we can write that V is equal to u plus at. In this time we can write the equation of motion, V is equal to u plus at. So V will give us the velocity at the final instant. Ui is the initial velocity, okay, that is the velocity just after the collision, right? U is the velocity just after collision, because that is the time we are starting our clock. Okay, starting is just after collision and some time Ti after it. This time will be, time interval is Ti, 0 to Ti, right? And acceleration we already know, and this is V, the final velocity. So we'll say that final velocity is some Vi for the ith electron. So that's why we are using the index I. Okay, it is for a particular electron, let us say ith electron. Okay, so initial velocity, let us assume the initial velocity just after collision to be Ui. Okay, just after the collision, after the latest collision, the recent collision, the velocity was Ui. Okay, acceleration, we know the acceleration is only due to the electric field over here, so it is E by m, right? And we can say this is all our vectors, so I'm just dropping the vector sign. Finally we'll bring it back because we know it's all vectors. And finally the time that has passed from the last collision to the time that we are recording is Ti, right? Ti has passed after the last collision. Okay, so this is the expression for final velocity, which is what we are supposed to find, final velocity of the electron after it has suffered the latest collision. Okay, now we have to take the average, right? This is for a particular electron. This I index is showing that it is for the ith particle, okay, ith particle or the ith electron. Okay, so now we have to take the average over the all the electrons that are present in the conductor, which are moving like this. Okay, so if we take the average of the initial velocities, so if we take first of all the average of this, we'll say basically average of UIs will actually give you 0 because it is random, right? Every electron, the initial velocity just after collision, right? UI is the initial velocity after collision. So one electron might be moving that way, one might be moving that way. So the net effect basically will cancel. Okay, this is an assumption. Is it completely true? Over the bulk, it seems good to be holding. Okay, so the average velocity over the entire bulk or the just after the collision will be 0. So this term will be going to 0. Okay, now we'll be left with EE by this time average. Okay, we also have to take the average for all the times. Okay, the time that passes after collision for different electrons, and actually we had defined a term for this in the concept class. In the previous class we said that we defined a term tau, right, which was the relaxation time, which was the average time between two successive collisions. Right? Tau is average time between two successive collisions. So since this time average is the time after collision, this tau, so if you want the average of that, it will be nothing but tau, which is the average time between successive collisions. Okay, so this will basically become tau. That is what I am saying. So this is the final velocity, final average velocity that we want, with which the electron is drifting. So we can call it to be the drift velocity. And here we have this Ti can be replaced as your tau, right? The average time, or the relaxation time, or the average time between two successive collisions. So this is time between collisions. Okay, so you have to basically find the average of that. So that will be relaxation time, and this is the expression that we obtain for your drift velocity, right? It is a constant velocity, and here you can see that you can put the vector signs too. So drift velocity will be minus E tau by m. Okay, this is how you are um, introduced to this derivation in your NCERT. Is it 100% through? God knows. Okay, so that's about drift velocity. Let's move to the next derivation now. Find the relation between your current and Vd, and hence also the relation between current density and the drift speed, which we just saw now. Okay, so I told you these three quantities are related: current, current density, and Vd. Okay, drift speed. And the relation between current and Vd, we saw it in the last class, is NEAVD, right? So we'll be deriving it in this class. So again, we'll assume a conductor. Okay, and suppose there is an electron which is moving, charge flow, current flow in this conductor, and it is, now we know that it is moving with certain drift speed, right, Vd. Okay, now this wire, suppose the conductor has a cross section area of A. Okay, so this cross sectional area is A, and the length, this length of the wire can be defined to be Vd times delta t, right? Delta t will be the time taken for this electron to move from this phase to this phase, right? Delta t is the time taken by the electron to move from this to this. Then length is equal to distance into time. Length, the distance is equal to speed into time, right? So speed is Vd and time is delta t. Delta t is the time taken for the charge to move from this phase to that phase. Okay, so basically this length of the wire, the length of your conductor, can be expressed as Vd times delta t. Okay, now we'll begin the derivation with the number of electrons, considering the number of free charges, okay, in this system. Okay, so basically small n, we use it for number density, okay, which is the number of free electrons per unit volume. So this is free electrons per unit volume, and capital N will use for number of electrons. Okay, this is not per unit volume, this is basically number of electrons. Okay, so this is number of electrons. Okay, so basically this number density can be expressed as capital N by V, right? So this is the number of free electrons. Okay, so now let us find this capital N in terms of this number density. So number density is N, right? So if you multiply it by volume, that will give you capital N. Free electrons basically will be volume times your number density. Just like your what we can say mass is equal to density into volume. So number is equal to number density into volume. Okay, just like that. Okay, so I hope the logic is very clear now. And what we'll do, we want this n in the derivation, because the final thing that we are supposed to obtain is this. I hope you remember this relation from the last class. Okay, so we are supposed to reach there. We want this n, the number density, it's present in the formula. This volume, however, is not there. Volume can be expressed in terms of area and length, right? So we can say volume is area times length. So area, if you see, we have chosen the cross section area is A. Let's keep it as A, and the length is nothing but the drift speed times the distance, right? Sorry, drift speed times the time interval. Why am I saying distance? Okay, so this is your number of electrons, number of free electrons which are present in this volume. Okay, I hope so far it is clear. Now let us come back and now we have to go to the current, right? So we can find the amount of charge now. We know the free charges, right? Amount of number of free charges. We can find the charge due to them. Okay, delta Q. Delta Q can be found out easily, which is basically N into E, right? Number of free charges into the charge, the intrinsic value on charge, the smallest charge, right? Delta Q is N into E. So N, we know that it is N A V D, and delta T also we have, and capital N E. Okay. Now if you want to find current, current is basically, you can see it over here, delta Q by delta T. Okay, so you can divide this by delta T, or you can bring this delta T over here. So that will give you I is equal to NEA. So I'm clubbing this together, NEA VD. Okay, this T comes down over here, right? So this is nothing but definition of current. We learned it just previously, and this is I is equal to, so that gives us I is equal to NEAVD. Okay, so this is the relation between your current and drift speed. Also, you can go one step further and find the relation between your drift speed and your current density, because current density is I by A, right? Current by A, by magnitude. Okay, so if you take I, so which is NEAVD divided by A, okay, so that will give you J is equal to NEVD. Okay, so these two are the expressions, the relations for current density and your current in terms of drift speed. Okay, very important relations, and yeah, that is how you derive them. Over to the next derivation. So knowing what we know now, we can surely derive the derivation for Ohm's law, but can you do this? Let's come back to Ohm's law. So I is equal to NEAVD. We know the relation between current and drift speed. So drift speed is also given as E tau by M, right? So we will only consider the magnitude, since current is a scalar quantity. We are not worried about the sign. So let us substitute that VD in your current definition. So NEA E tau by M. Okay, so this will give us, if I write it like NE square tau and by M. Okay, this term has a special meaning, that's why I am writing it in parenthesis, actually the reciprocal of it, if you can remember it from the previous class. So NE square tau by M. So we are left with A and E. Okay, now for a constant potential, we can express it as V by L. Electric field can be expressed as V by L, right? So for a constant potential, it is basically the potential across that particular length. Okay, so I will be given as NE square tau by M and A, and here we'll have V by L. Okay, V by L. Now I can take this everything to the other side. You can see that V and I, we have already obtained them. So V is equal to, we can say M by NE square tau. So this term, if you can remember it from the previous class, and we have L by A, and we'll have I, right? So you can see that all these are constant, M, N, E, even tau, L and A, the length and the area of the cross section. So you can see that V and I are directly proportional, or V is equal to IR. Now how does this R appear, the resistance? It's basically constant for a material. Okay, but you can remember from here also, we discussed this term in the previous class. It was resistivity, right? M by NE square tau. Okay, and R is nothing but resistivity times length by area. So resistivity times length by area, R. Okay, so that is how you get R over here, the constant as R. And if you see this term, you are supposed to remember that this term is resistivity. Okay, this term over here is resistivity. Now we can go one step further and we can derive Ohm's law in vector form. So we can say I by A, from actually here we can say I by A is NE square tau by M. Now this you know that it is the reciprocal of resistivity. So 1 by rho, and are we missing something? Yes, E. Okay, now I can write it in vector form because I want Ohm's law in vector form. I by is nothing but current density J, and you can see that E can be written as rho J, right? This is Ohm's law in vector form. This is Ohm's law basic, and this is in vector form. Okay, I hope the camera has recorded because I'm doing this derivation for the 4th time now. I'm also doing that for the 4th time now. Okay, so that's about this derivation. Over to the next one. Come to combination of resistors. So we have series and parallel combination. So let us derive the expression for equivalent resistance in both the cases. So for series case, we know that the current through both the resistors which are there in series will be the same, right? There is no branching of the circuit, so same current will flow, and only the thing that is splitting over here is the voltage. So across this resistor we have V1, and across this we have V2. Okay, so actually this V will split into V1 and V2. We can write V is equal to V1 plus V2, right? Now we can in place of this R1 R2 series combination, we can have an equivalent circuit wherein we have R equivalent and the same voltage source V. Okay, so this V can be written as the same current will come out of the circuit, right? So V is equal to I into R equivalent from this circuit, right? V is equal to IR. Now coming back to the circuit, we can find V1 and V2. V1 will be the voltage drop across R1, which will be IR1, and across V2 it will be IR2, right? So you can see that the current will be the same. Basically, since this is the equivalent circuit, same current will be drawn in both the cases. So I will cancel out throughout. So R equivalent will be R1 plus R2. Okay, or in general, if you have n series resistors, then R equivalent will be R1 plus R2 plus so on up till Rn. Okay, you just add the resistors which are there in series to obtain the equivalent resistance. Okay, so this is the equivalent resistance in series. Coming to parallel combination, here the thing will be different because I will split, right? The current will split into I1 and I2. Okay, so equivalent, we have basically the same equivalent. In place of R1 R2 parallel combination, you replace it by R equivalent. The same thing is gonna happen. It will derive a current I from your I from the voltage source. Okay, but it won't be as significant as in the previous case because here the current is splitting, right? So I can say I is equal to I1 plus I2. Let me check if the camera is recording. Yes, it is. So I is equal to I1 plus I2. So in this case, we can write it from there. So V by R equivalent, right? I is equal to V by R, Ohm's law. Okay. So I1 will be V by, so here if you see this, both resistors are connected across the same potential V. That is what is meant by parallel combination, right? So again V by R1, right? And this current I2 will be V again across this resistor, it is V by R2. So you can see that 1 by R equivalent, V can cancel throughout, is 1 by R1 plus 1 by R2. Okay, or in case of two resistors, you can directly remember it is product upon sum. Okay, so you just have to take the product and then the sum. Okay, then reciprocal, right? So product upon sum. If you simplify it further, okay, take the LCM, and on top you will get sum, down you will get product, and then reciprocal. Okay, now in general you won't have formula in this format. In this format only you will obtain. So 1 upon R equivalent is 1 upon R1 plus 1 upon R2 up till so on plus 1 upon Rn. Okay, so this is for in general n resistors in parallel. Okay, so that is for series and parallel combination, the relations for the equivalent resistance, and that is how you derive it. Over to the next one. Let's come to the derivation on cell and internal resistance, basically the relation which says V is equal to E minus IR. So you'll see that derivation is a piece of cake when you apply your Kirchhoff's law. So we'll choose the path. You can also choose a loop and a path in Kirchhoff's law. There is no such rule. Okay, so we can choose the path from B to A. Okay, so we are moving from B to A, and we'll find a relation for the voltage difference between B and A. Okay, so starting at point B, the potential, let us suppose at point B is VB. Okay, now current and your resistors, we are, remember, we are moving from B to A, right? We are moving in this direction, so current and your sense of direction is the same, which means there is voltage drop, right? So if you are along the current, there is minus IR, right? Voltage drop. Now you are moving from negative to positive when you come to E, so that is plus, right? Gain. Negative to positive, lower potential to higher potential, gain. And finally you will come to VA, so this will equal VA. Okay, you can see that E minus IR, E minus IR will be VA minus VB. Okay, the potential difference. So I can write VAB is nothing but E minus IR. So this is how we obtain V is equal to E minus IR. Okay, so very simple derivation, right? So we'll discuss three different cases. So first is when I is equal to 0. So you're not using it any circuit. Okay, it is just left open. So when I is 0, you can basically see that VAB will be basically equal to E. The potential drop across AB will be nothing but the EMF of the battery. Okay, since there is no current in the internal resistance, whatever voltage difference across the two ends of the battery is the same as your EMF. Okay, VAB is equal to EMF when the battery is under no use, when current is 0. Okay, next case we'll take when A and B are short circuited, or when VAB is 0, okay, which means A and B are short circuited. So basically you connect points A and B using a conductor. Okay, so if you connect A and B using a wire, basically their potentials will be same, right? If you connect these two by a wire, potential at A and potential at B, basically they become the same point and their potential will be 0. Okay, so VA and VB will be equal, and VA minus VB will be 0, or VAB will be 0. Okay, so if you say AB is short circuit or VAB is equal to 0, it's the same thing. So if VAB is 0, you can see that the potential, the EMF of the battery will drop across the internal resistance. VAB is 0 is equal to IR. Okay, final case, if we had the battery charging, okay, instead of battery driving the circuit, the battery is drawing current. So battery charging, so in this case we'll have battery is drawing current. So if we move from VAB and we have R, so the current is going inside the battery. So you can see the relation that we are going to obtain over here is VAB is E plus IR. Okay, you can derive it. I'm just checking it. You'll obtain like this. Okay, VAB is E plus IR. Let's try it. Okay, so VA, again using Kirchhoff's law, now we are moving from A to B. So this is E, that will be minus E, right? We are moving from higher potential to lower potential, so that is minus. We are moving in the direction of current, minus IR, and finally we'll get VB, or we can say VA minus VB is, okay, take this go to the other side, E plus IR, right? So VAB is E plus IR. Okay, so this is in case of charging of battery, which is very rare. Usually battery drives the circuit. So this is the most common, that one, the one which you should remember. Okay, however, don't forget this. This is also possible wherein the battery is charging. Okay, so that was about the internal resistance and the EMF of a cell. Let's move to the next derivation on wheatstone bridge. Now come to the wheatstone bridge, we will be deriving the balance condition. I told you in the previous class that you could derive the balance condition, which was P by Q is equal to R by S, different resistances over here. So you could derive this using Kirchhoff's law. So if you don't know about Kirchhoff's law, I would suggest that you go and check out the previous video on Kirchhoff's law, wherein the video on all the concepts. So the links are available in the description. Okay, so we'll be using Kirchhoff's law to derive the balance condition of a wheatstone bridge. Okay, so we are assuming that current I is entering this bridge. Okay, so it will split over here at point A into I1 and I2, we can say. Okay, so I1 will reach at point B, and again it has to split, so we'll split it. So some amount is going here, right? It is the galvanometer current. Under balance condition this will be 0, but let us assume it some, in general way, some current is flowing through the galvanometer, Ig. Okay, and this one will be I1 minus Ig, right? So I1 is coming over here, Ig is going over here, so this is I1 minus Ig. Okay, similarly I2 is over here. Now Ig is coming from this branch, you don't have to break I2 over here. Now Ig is already in this branch, so I2 plus Ig you will get in this branch, right? So I2 and Ig, so this is I2 plus Ig. Break the current only when there is no current in the branch. Okay, so we get the current in the different branches. Okay, and finally if you add this I1 plus I2, that will give you I, right? I splits into I1 and I2. Finally this, if you add Ig cancels, I2 plus I1, which is I. Okay, so current in going and out coming is the same. Now we have to apply Kirchhoff's law. Again, those who don't know about this, go check out the previous video. So we'll choose a loop, not path this time, this is loop. Loop A, B, D, A. Okay, so first we are going to choose this, then we'll choose this loop, and we'll obtain the balance condition. Okay, so A, B, D, A. Okay, A, B, D, A. So let us apply Kirchhoff's law. So going from A to B, we encounter this resistor, and it is in the direction, so I1 minus I1P. Okay, in the direction of the current, negative voltage drop, right? So again coming to this branch now, B to D. B to D we have a galvanometer, and this G is the resistance of the galvanometer. So current is Ig, and we have G, and we are moving in the direction of the current, so again negative Ig, G. Okay, come over here, we are moving from D to A, and current is in the opposite sense, so positive, right? Opposite to the current, positive, I2 times Q. Okay, so we are applying KVL over here. You don't know, sum of the voltages is equal to 0 across a loop, right? This is voltage across this, voltage across this, voltage across this. Okay, with proper convention. Okay, so this is equal to 0. Let's come to loop number 2, which is this loop. We can start from C, B, D, C. Okay, C, B, D, C. Okay, so now starting from C to B, we have this resistor. We are moving opposite to the direction of current, so you can say it is minus I1 minus Ig into R. Okay, I1 minus Ig into R, and then we are moving from B to D. We are moving in the direction of Ig, right? We are moving in the direction, so again it's minus Igg. Okay, and finally we are moving from D to C. We can see that we are moving in the direction, so again it is negative I2 plus Ig into S, right, is equal to 0. We can open this up, we'll name this 1. Let's open this up. This is minus I1R plus IGR minus IGG minus I2S minus IGS, right? So this will be equal to 0, and this is our equation 2. We can add 1 and 2, add 1 and 2. So if we add, we'll have minus I1P plus, minus IGG plus I2Q minus I1R plus IGR minus IGG minus I2S minus IGS is equal to 0. Okay, hope this is correct. Okay, so now what we'll do, we'll say that Ig is 0. Okay, actually you could have begun with the condition itself. Instead of considering this Ig everywhere, you could have initially considered it as 0 and again reach as the equation which I am going to show you now. So this Ig equal to 0 means this is 0, this is 0, this is 0, then what else is 0, this is 0. Okay, so we'll get minus I1P plus I2Q, and we have minus I1R, and we have minus I2S is equal to 0. Okay, so let me check that. I think we made a mistake over here. Since we were moving from C to B, it is opposite to the direction of current, so no need of this minus sign. Okay, so this will be plus and this will be minus. So I1R, so this is plus and that is minus, so which is Ig R, right? So this is minus, anyways that is 0, that won't affect, but this we have to consider, so this is I1R. Okay, so now you can take I1 common from here. So I1, if you take common, you have R minus P. Also you can take I2 common from here, I2 common from here, so that will give you Q minus S, okay, is equal to 0. Now we can say that, what we can say, we can take this to the other side. So I2 Q minus S is equal to I1, and minus sign we can take it in and we can say P minus R, right? So one of the equations that we obtain, this is equation 3. Okay, now also we can obtain one equation when we say Ig is equal to 0. So when Ig is equal to 0, if you see what will happen, let me draw this again so that you can see its simplified version. Okay, so when Ig is 0, this current is 0, whatever current is in this branch will also flow over here, right? I2 will flow again as I2. Okay, basically Ig is 0, so this will be I2, this will also be I2, this will be I1, this will also be I1, because current is not breaking at this point. So I1, whatever current goes over here, it comes off the other end, and I2 without breaking or without addition from that branch remains I2 over here. Okay, so we can say the current in this top branch is same, I1, and current in the bottom branch is same, I2. Okay, or we can say they are in parallel combination, right? These two and these two are in parallel combination. These two together and these two together, the upper branch and lower branch, are in parallel combination. So the voltage across them is the same. Or if you see these 2 points, the voltage across those 2 points is the same. Okay, so we can say this is P and Q, right? This is P, this is Q, this is R, this is S. So we can say I1 times P plus R, and okay, we'll do I1 into P plus R. So this is the voltage drop in the upper branch, I times R, P plus R, right? And the voltage drop in the downward one is I2 into Q plus S. Okay, now if we take the ratio, now this is simple, we obtained this relation when we considered Ig as 0, and we obtained it by equating the potentials, right? Because these two are in parallel combination. Okay, so now we can divide these two and we'll get Q minus S upon Q plus S is equal to, fine, what will we get? P minus R upon P plus R. Okay, now you can use your componendo and dividendo rule, which you might have learned in your lower classes. Okay, you can note this down. I'm going to erase off a certain part. Okay, so this is the expression that we obtain. So this is a long derivation. Okay, so now we can say, so basically if you have numerator upon denominator, you can write numerator plus denominator upon numerator minus denominator. Okay, this is the same fraction as numerator upon denominator. Okay, if you didn't understand, basically you can write numerator, so we have numerator plus denominator, okay, and numerator minus denominator. Okay, this is the same as this. Okay, it's no change, it's by componendo and dividendo rule. So again, P minus R numerator plus denominator, which is P plus R upon P minus R, minus P plus R. Okay, so if you simplify this, what will you get? S and S will get cancelled. You will get 2Q divided by this. What will you get over here? QQ gets cancelled, minus 2S, and here you will get RR cancelled, 2P upon what do you get? What do you get? What do you get? This R and R will get cancelled, minus 2P. What? P and P will get cancelled, and you will get minus 2R. So 2 can cancel out, okay, and this minus sign can also go. So we have P upon R is equal to Q upon S. Very much similar to your balance condition, or you can write this as P by Q, this interchanging R and Q is R by S. This is nothing but your balance condition, right? P by Q is R by S. Okay, so that is how you obtain the balance condition for wheatstone bridge. That is the derivation behind it. You use Kirchhoff's law and go on solving it. Use componendo dividendo at the end, and this is also a crucial step wherein you equate the potentials, and that's about it. So over to the next one. Come to joules heating over here. So it's very easy derivation. I think we also briefly discussed it in the concept class also, because it's very simple. We'll assume that the amount of charge that moves through a delta Q is the amount of charge that moves through a potential V. Okay, so some amount of work is done over here. Suppose this action happens in some time delta t. Okay, so the amount of work delta W is given as V times delta Q, right? So this is by the definition of potential, right? Potential is work by charge. So the amount of work done in moving delta Q through potential V is dW is V times delta Q, right? So we can take we can divide this by the time interval. Okay, now we know this as our rate of work is power and V, and this is nothing but average current, right? Delta Q by delta T is I. Okay, so this is nothing but the expression of power. Okay, we want heating expression. So for now we can also express power as V can be written as IR, so this can become I square by R, or I can be written as V by R, so in that case it will be V square by R. Okay, so these are different relations of power, and heat is basically power times time, right? Heat is energy, energy is power times the time taken. So power times time will give you the heat. Okay, so you can say it is VIT, or you can also say it is I square RT or V square by R into T. Okay, whatever expression you want. So this is about joules heating. Now we are only left with one derivation, which is about the grouping of cells. There are three different types. So first we'll do two of them, and finally the last one, which is the mixed grouping. So that's about joules heating. I hope that is very simple. Let's move to the next one. Of cells or combination of cells. Here we have cells in series combination with their respective internal resistances. Okay, they are all equal cells, same cells. So each one has EMF E and internal resistance R. We also have an external resistance capital R, which is present there in the circuit. Okay, we are supposed to find the what is the net current due to this type of an arrangement. Okay, here we have a mixed one. The parallel one is also very simple because the EMF remains the same. We'll be discussing that next. Okay, so let's come to the series one first. So if we want to find the net current, basically I net, for that we need your EMF, net EMF and R equivalent, right? So let's try to find them first. So if you see all the cells are in series. Okay, what will be the potential drop across this? It will be nothing but N times of E, right? E plus E plus E plus E. If you apply Kirchhoff's law and move from A to B, so you'll have you are moving every time from negative terminal to positive, right? Negative to positive. So E plus E plus E plus E. So that we have N times of E, N cells, right? We are doing it for N cells. So N, the net EMF is N times of E. So similarly, R equivalent, if you see, is nothing but all these resistances are in series. Again, you can use Kirchhoff's law. You'll see that or you can see that the same current will be flowing through all these resistances, right? Even the R1. Okay, so all of them are in series. So same current is flowing, meaning they are in series, right? So R plus R plus R is NR plus this external one. Same current is flowing. This is not in parallel. Okay, this is in series. Okay, so you can write I net is N by E upon NR plus R. Okay, let's come to the mixed case wherein we have cells in parallel combination as well as in series combination. So in series we have n cells, and again in parallel we have m branches. Okay, so n cells of, then we have m branches. So in the second branch also we have n cells in series. Okay, in the third branch we have n cells in series. Okay, so this pattern repeats up to m branches. Okay, now let us find the I net in this case also. So in this case, first of all, we can see that E equivalent will be nothing but n times of E. Okay, so if you see the 2 points over here again, and if you apply Kirchhoff's law, it will be E plus E plus E plus E up to NE, right? And in parallel combination, E does not change. Okay, that is a point that we'll emphasize later also in parallel combination. So if you have two cells in parallel, E and E, they won't change the EMF. Okay, the potential difference across these 2 points will be E only. Okay, so it won't change in parallel combination. In series, it adds, right, due to Kirchhoff's law. In parallel combination, it will remain same as in one branch. In one branch, we have NE. So here also it is NE up till in every branch it is NE. Okay, so equivalent EMF is NE. M does not have any effect. If we increase the number of branches, it won't have any effect on the equivalent EMF. Okay, because EMF in parallel it does not adds up. Okay, in series it will add up. So equivalent EMF is this. Now let us come to equivalent resistance. Okay, so if you see in one branch, this N resistances are in series, but this NR branches are there in every. So if I had to draw this, it is NR branches in M branches, right? NR resistances in M branches. So you'll have a case like this. Okay, so if you add all the resistances in the one branch, you'll get NR, 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 NR like this in every branch. Okay, there are M branches. Okay, so it will become NR by M, because R, if you have R and R in parallel, if you two equal resistances in parallel, it becomes R by 2. Okay, similarly if you have R in parallel, it will become R by 3. So if you have NR in parallel M times, so it will become NR by M. Okay, the equal resistance is divided by the number of rows, number of branches, and plus don't forget this one, the external resistance plus R. Okay, so I net will become NE by NR. Did you hear the bell? The bell is a little funny. Okay, it screams like a monster. Anyways, so that is the net electric current that you get from this type of an arrangement. Do let me know in the comment section what is the max value or the condition for the current to be maximum in this case. Okay, I think I mentioned this in the previous class, but anyways, do let me know in the comment what is the condition for maximum current in this type of arrangement. And let's move to the last arrangement, which will be the parallel one with two different cells. Okay, so let's discuss that. The final derivation for the day. Here we have two cells in parallel combination. They are different cells. E1 and E2 are separate. R1 and R2 are separate. Okay, so we'll discuss this in a general way, and finally you can go to the specific case where two cells are in the two cells are identical. Okay, you can put E1 is equal to E2 and R1 is equal to R2 in the final result, and you can obtain the relations for two identical cells in parallel combination. Okay, so how we are going to proceed with this? So first of all, let us say that the current in the first branch, this is the current I. Okay, so I is going like this. Okay, I is coming from here, it is going like this. Let us say that it splits into I2 over here, and I1 over here, it splits, this I splits into I1 plus I2. I can write I is equal to I1 plus I2 using KCL. Okay, now again we are going to use Kirchhoff's law. So if you are not proficient at it, if you're not skilled at it, go watch the lecture on the one-shot video on current electricity. Okay, so first we'll choose this branch, okay, the outside branch, and then we'll choose the inside branch. So in first case we'll get I2, in second case we'll get I1, and we'll get net I, the net current I, as I1 plus I2. Okay, that is the logic behind what we are going to do over here. Okay, so let us find that. So let us first choose a loop D F A C D. Okay, D F A C D. Okay, so let's start from D to F, nothing is there. Then F to A, you have a resistor, and you are moving in the same direction as current, so minus I2 R2, and we have plus E2 since we are moving from negative to positive. Then we have A, then C, nothing there, A to C, nothing there. Then C to D, we have a resistor R, and the current flowing through R is I, and we are moving in the same direction, right? Same direction as that of current, so negative and equal to 0. Now from here I told you we are going to find I2, right? So I2 will be E minus IR, and I2 R2 we can say, right? So, or I2 we can say that E by R2 minus IR by R2, right? So this is the relation for R2. Let's obtain the relation for I2. Let's obtain the relation for I1. Okay, so I1 is in this branch, so we have to choose that loop D E B and C D. D E B C D. Okay, starting from D going to E, nothing is there. Then from E to B there are two components. One is a resistor, we are moving in the same direction as that of the current, so minus, then negative to positive, so plus E1, then moving like this, then moving from C to D we are moving in the direction of the current, right? Current, so, and resistor is R, so IR, that will be equal to 0. Okay, we are applying KVL over here. So now is there something wrong? So this is I1, right? Current is I1 in this branch. So we are supposed to obtain I1. So I1 R1 will be given as E minus IR. Okay, I'm just taking this to the other side. So I1 will be E1 by R1 minus IR by R1. Okay, so now we can add. Now we know that I is equal to I1 plus I2. So net current is I1 plus I2. So net I is this plus this. Okay, I1 plus I2. So we can club this together, E1 by R1 plus E2 by R2. Okay, and we'll also have minus IR is common, you can see minus IR is common, and we have 1 by R1 plus 1 by R2. Okay, IR is common, minus IR is common, and we have 1 by R1 plus 1 by R2. Okay, now you can generalize this actually, I net. So in place of those two cells you have n general cells. You can say the summation I running from 1 to n, or you can neglect the I. Basically you can write it in syntax only, E by R, right, minus IR summation 1 by R. Okay, so your basically the summation will run from 1 to whatever number of cells, n number of cells in parallel, suppose. Okay, so we'll have E1 by R1, E2 by R2 plus E3 by R3, so on up till En by Rn, and here also minus IR, and again 1 by R1 plus 1 by R2. So you can write this in a general way. Okay, now I can get this I to the other end. Now if you see, this I is the net current I, right? So no point in writing this I net every time. So I can treat this I as the net I, because it's I1 plus I2, the net I. Okay, this is also the net I. Okay, this is the current in this resistor, right? It is the net current. You can see that So bring that I to the other side, we can take common, right? So we can say 1 plus what is this, 1 plus r and summation 1 by r. Okay, this is what we get, right? If you bring this to the other side, we'll get, this will become positive, I can be taken common, so 1 plus r and this. Okay, and we have E. Okay, so the net current that you obtain is summation E by r upon 1 plus r into summation 1 by r. Okay, or we can actually divide everything by summation, we'll divide everything by summation 1 by r. Okay, so that in the denominator we don't have product of two resistances. Okay, what we'll do, we'll divide everything, the numerator and the denominator, by 1 by r. Okay, by summation 1 by r. So this is the numerator divided by summation 1 by r upon, okay, denominator. So if you divide 1, you have to divide by summation 1 by r, be very careful, and if you divide this by summation 1 by r, both of them will get cancelled and you'll get this. Now you can write this in the format of E equivalent by r equivalent. Okay, so that's why I divided by summation 1 by r. Okay, so this is the net current that you obtain, this is E equivalent and this is R equivalent. So equivalent can be written as summation E by R, and also you have upon, I think this is divide, right? We are dividing by summation 1 by R. Okay, this cannot be cancelled, this is summation everything E by R. Okay, this is only summation 1 by R, not E by R. Okay, it cannot be cancelled. Or in case of two cells, you can write it as E1 by R1 plus E2 by R2 in the numerator, and in the denominator we have 1 by R, so 1 by R1 plus 1 by R2. Okay, if this is confusing, please go again through the derivation. We found I1, I2, added them and then use the summation notation for the general case. Okay, so for two cells it is E1 by R1 plus E2 by R2 upon R1 plus R2. This is the equivalent what you can say EMF of this circuit, or and your R equivalent will be simply, you obtain it over here, capital R of course, plus 1 plus summation R1, so 1 by R1 plus 1 by R2. So this is the equivalent resistance. Okay, these are the two relations that you are supposed to remember thoroughly. Okay, and this is the net current that you obtain, this I equivalent, and if you want I equivalent, I net current, so you can divide this and this, that will give you the net current. Also now in the case where the cells are identical, okay, you can substitute E1 and E2 equal, R1 and R2 equal, and obtain, tell me what will be the E equivalent in case where these two cells are identical. Okay, what is the value of E equivalent when the two cells have identical EMF and identical internal resistances, so E and R. So E and R, E and R. Tell me the equivalent EMF, okay, in the comment section, and correct answer receives a heart. So yeah, that's about it. So that's all what I wanted to cover for today's lecture. I hope you really enjoyed it, and with that we finish all the derivations from the chapter of current electricity, and I'll see you soon in the next video. In the next video, I'm going to update you about what we are going to do next. Of course, we are going to continue with the series. Along with that, we are also going to have a new series for your competitive exams like BITSAT, JEE, NEET, and boards maybe. Okay, so we'll be planning on that. In the next video, I'll be updating you. That will be somewhere in the mid November. I hope you enjoyed this video. If you want to learn more about for your competitive exam, this channel is a gold mine for you, especially for BITSAT aspirant. There is already a lot of content available, and also we'll be making a lot of content for all the competitive exams that are going to come up next for the next year, for the year of 2024. So if you are somebody who is interested in this type of content, do consider subscribing. Thank you for making it this far in this video, and yeah, keep enjoying physics.